Hi, today I want to talk to you about creative coding, using creative coding as a doorway to learning to program, and interventions that we might carry out to support people who want to follow such a path. But before we get into that, we need to define creative coding. It's difficult though, because creative coding means different things to different people. For some people, it means things like Twitter bots, via things like the generative language tracery. Some people might use the term to just refer to procedurally created art generally, such as through the Markov Jr. programming language. While others still might take it to mean things like controlling synthesizers through esoteric programming languages, such as in Orca, and just lots of other things besides. We can make a modest crosscut through this space by focusing on the particular tools used for this activity. Processing is among the most well-known of such tools. It first appeared about 20 years ago and made it easy for artists, or really anyone, to make code through a simplified Java interface. What you see here is basically the hello world of processing, circles generated by moving the mouse. This language became immensely popular, and it led to a huge number of artists and lots of other people besides learning to code and just making procedurally generated artwork. Part of what made this language so approachable was its simple to use integrated development environment, which made it quick and easy to get going. Jump forward a few years, and with the meteoric rise of JavaScript, along comes an adaptation of processing into JavaScript through a library called P5. Like its predecessor, P5 provides a welcoming environment for anyone wanting to learn to code, especially those not coming from a traditional computer science background, as well as an even easier to jump into web-based editor. The inclusive tendencies found in creative coding and surrounding communities, such as those of P5 and processing, have been the basis for a large number of introductory programming classes. So, this combo seemed like a good basis for a course targeted at those who are left out by the often overly abstract topics found in most Intro CS courses, such as those found in our own department. So, we started teaching a brand new course called CS 111 that focused on using creative coding as an introduction to programming. This course used P5 flavored JavaScript to teach introductory programming concepts such as syntax and abstraction and motivated by art-type topics. This course focused on non-majors with little to no experience. We ended up supporting students from 22 different non-computer science majors. Being researchers, we took this as an opportunity to answer some questions that we had about what types of tools would help novices in such an environment. In particular, we wanted to know how to enhance standard tools so as to improve students' creative powers, as well as what types of features would be perceived as useful in such a situation, based on the premise that if something isn't perceived as useful, then it probably won't be used. To answer these questions, we taught the course a number of times across 2 years, twice during the school year to undergrads, and twice during the summer to high school students. In the first year, we made minor modifications to the base P5 editor to accommodate the particularities of our course, such as submission to GitHub Classroom through the editor and the like. Then, during the course, we ran a logging study where we captured each time code was executed, and ran a post-course survey about what features were meaningful and what students thought of a number of speculative features. Based on the results of the first year of studies, we made a number of modifications to the editor. These included introducing components like color pickers, number sliders, autocompletes, among a variety of others. In addition, we introduced some more unusual features, such as the ability to bidirectionally manipulate graphic and text. This feature is called the shape toolbox, which we see here. By typing the editor.shapetoolbox command and then clicking open, the user can now create compositions of simple shapes and lines, such as through circles, squares, and beziers. Once done, the user can click Save, which will create corresponding P5 commands in the text editor. Users can move back and forth between these views as they wish. We wanted to understand the effect of these changes, so we again ran a logging study and a post-course survey, covering opinions about the utility of these features and how they affected student learning. Analyzing the collected logs and surveys across the 4 course offerings, we found 4 key results. We found that static analyzers, such as linters, were seen as valuable in learning to code. Live programming features can be seen as annoying, overwhelming, or even impolite. While some features were seen as useful, their value was sometimes limited by the perception that they cluttered the interface. And finally, we found that some features may be perceived as being too useful. Now, let's take a brief tour through some of our findings. To start, let's look at static analysis. We found that simple and understandable advice, like those surfaced through static analyses, were well regarded. In particular, polite, lightweight assistants that respect the user's agency, like those expressed through linting and auto-formatting, can be a helpful platform on which to learn and test new skills with confidence. On the other hand, one student noted that they would prefer to do things by hand rather than use advanced features because they lacked clear visual indicators of a particular action's effect, highlighting the importance of clear effect forecasting for feature trust. Next, we observed that overeager evaluation can overwhelm and stress users through distracting updates that are unsynchronized with their experienced edit-run cadence. Live programming offers enticing benefits for novices and for creative applications. For instance, feedback immediacy and a closeness of mapping between code and graphics is clearly useful in such contexts. We found that while live programming was well accepted by some, it needs to be carefully tuned to be not perceived as annoying or distracting. Next, let's talk clutter. Making values directly manipulatable has long been a hello world type feature for live programming environments. As live programming was a part of our design approach, we implemented a couple of such features, allowing for sliding and picking of numeric values. Interestingly, a number of students found that such tools were messy and disrupted the look of the code, which often led them to not using those features or just even turning them off entirely. We suggest that while such features can be valuable in some cases, their value may be overstated in others, particularly such as our context. And finally, we come to skepticism. A number of students expressed concern that some of the introduced features would impede their learning, noting that tools like autocomplete might prevent mistakes in a way that prevents students from learning the commands themselves, or that direct manipulation might cause students to skip the sweat that makes up learning. While these views are important in that they highlight the types of features that students might believe are useful and therefore end up using, we note that students who are given improved tools simply worry about the plenty of challenging learning left to do. We found that once students got their hands on the tools, they ceased to be skeptical about them and they sort of just faded into the background. We view this situation then as being akin to giving students calculators in a math class. They help with specific classes of tasks that, once simplified, enable learning about richer topics. Now touched on the 4 key themes in our results, ranging across static analysis to skepticism, but of course there's more to say about each of these, and other things besides. For instance, one of our research questions was about how these tools affected creativity. So, what about creativity? Well, we found that there are 2 useful categories of interventions in this regard. First, we found that automating tasks that impede creativity has a lot of leverage. For instance, students felt that tools, like our Shape Toolbox, were able to reduce the friction between ideation and reality for a number of creative tasks. It's just much easier to get something to be pixel perfect if you can just place it there. And second, we found that it was particularly useful to help users figure out how to do things that they didn't know how to do, or that were even possible. That is, transforming unknown unknowns into known knowns. While things like reading the documentation can be useful, integrating such knowledge directly into the editing environment can reduce some of the burden derived from context switching. There's tons more interesting work left to do in this space, and this suite of studies only scratches its surface. In future work, we intend to talk to people on the other side of the classroom, as teachers, about what it is important to them for teaching creative coding, and reciprocally, what are the tools that teachers make for themselves, and why do they do that? Our Shape Toolbox provided a lot of power, but there's lots of additional adaptations we might make to such an editor, such as through structure editing and richer bidirectional tooling. And finally, we mostly focus on perceived utility rather than learning effects. So in future work, we intend to consider the effect that this style of technical intervention has on learning, rather than only on creativity and perceived utility. There are lots more details about our findings and our study, so I encourage you to check out this link to learn more about this project. Thanks for your time and attention.